Welcome to the FAR Training Hub.
It's good to be here.
Today we are rolling up our sleeves and getting our hands dirty. Metaphorically, of course.
Though for a lot of our listeners, it's probably quite literal. Grease and grime.
That's true. We are tackling a subject that is, and I don't think this is an overstatement, the absolute backbone of the trade. If you're prepping for your ARPL assessment, the artisan recognition of prior learning, this is it. This is the module.
It really is. We're talking about materials, the MA module.
And it so often separates the hobbyists from the true artisans.
It's the starting point for everything. You can be the best welder, have the steadiest hand on a lathe, but if you don't understand the material you're working with, you're just flying blind.
It's not just theory for a test, is it?
Not at all. This is the stuff that determines whether what you build stands for 50 years or, collapses in a week.
Exactly. I was thinking about it like this. It's like ingredients in a kitchen. You wouldn't try to bake a cake with salt instead of sugar, just because they're both white crystals.
That would be a very memorable cake, let's say.
Right. A disaster. And in the workshop, confusing cast iron with mild steel isn't just a small mistake. It's a safety hazard. It's a broken tool, a failed assessment.
A big deal.
So that's our mission today. We're going to crack that code. We want to unpack why materials behave the way they do, so you're not just guessing.
And the best place to start really is what I call the Great Divide. In the world of metals, there are two main families.
Okay.
You've got your ferrous metals and your non-ferrous metals.
All right, let's start there. Ferrous. It sounds a bit intense.
Well, it comes from the Latin word for iron, so it's actually quite simple. Ferrous metals are just metals that contain iron as their main component.
Okay, so if a magnet sticks to it.
It's almost certainly ferrous. Or if you leave it out in the rain and it rusts, that's another dead giveaway.
And non-ferrous is just the opposite.
The opposite. No iron. They're generally non-magnetic, and they're much better at resisting corrosion. They bring a whole different set of properties to the table. But let's stick with the heavy hitters first.
The iron giants.
Exactly.
So I was looking through the notes, and it seems like pure iron, just on its own, isn't actually that useful to us.
That's right. Pure iron is surprisingly soft. It's made of ferrite crystals. If you tried to build, say, a machine bed out of pure iron, it would just dent and bend. It wouldn't last 5 minutes.
So we have to add something.
We have to add the magic ingredient.
And that would be carbon.
Carbon is the key. It completely changes the behavior of the raw iron. Think of it like a spectrum. On one end you have steel, and on the other you have cast iron.
And what divides them is a really tiny amount of carbon. I see a number here, 2.5%. Is that right?
It's a tiny number, but it makes a world of difference. That's the rule of thumb. If the carbon content is less than about 2.5%, it chemically combines with the iron. It forms something called iron carbide.
And that gives us steel.
That gives us steel. But if you push that carbon content higher, say up to 4%, the iron basically says, I'm full. It can't absorb anymore.
So the extra carbon just sits there.
It does. It forms little flakes of graphite inside the metal, and that mixture is what gives us cast iron.
See, that's the part that always felt a bit backwards to me. Cast iron has more carbon. I always just assumed steel was stronger, so it must have more of the tough stuff in it.
Well, it depends on how you define strong. That's a huge thing for an artisan to understand. Cast iron is incredibly strong in compression.
Meaning you can pile weight on top of it?
A lot of weight.
Yeah.
But it's brittle. Because of those graphite flakes, it has very low tensile strength. If you try to pull it,
it snaps.
It snaps.
And for the trade test, there are two main types to know. Gray cast iron and white cast iron. Let's start with gray. I assume it's called that because...
Because it's gray. When you break it, the fracture is gray. Not very imaginative, but it works.
Okay, and the properties.
So those graphite flakes we mentioned, they're not just a bug, they're a feature. They make gray cast iron self-lubricating.
Wait, what? Self-lubricating, so you don't need cutting fluid when you machine it?
You don't. And anyone who's machined it knows the feeling. It cuts so easily you get these black crumbly chips. The graphite acts as a built-in lubricant.
That's amazing.
And it also gives it this fantastic ability to absorb vibration. We call it damping capacity.
Which is why we use it for machine beds and engine blocks. You don't want your lathe ringing like a bell.
Precisely. The cast iron just goes thud. It swallows the energy. But remember the trade-off. Drop it, and it might just crack in half.
Got it. So what about its meaner cousin, white cast iron?
White cast iron is a different beast. Less silicon, a bit less carbon. But the huge difference is that the carbon is in the form of iron carbide, not those graphite flakes.
Which I'm guessing makes it hard.
Extremely hard. And brittle. You can't really machine it with normal tools. You have to grind it, We use it for things that need to grind other
Like
things.
crushing equipment or cement mixers.
Exactly. Grinding balls, liners for mixers, things that need to stand up to incredible wear.
Okay, so gray for damping, white for wear. Let's slide down that carbon scale now to the stuff we use every day. Steel.
Right, and it's not just steel. The carbon spectrum here is everything. Tiny changes in percentage completely change the metal's personality. We usually break it down into low, medium, and high carbon.
Starting with low carbon steel, which everyone just calls
Mild steel.
mild steel.
Yeah, this is your workhorse.
Wow.
We're talking 0.15 to 0.3% carbon. It's tough. It's ductile, meaning you can stretch it into wire.
And crucially, it's easy to weld.
Very. It's forgiving. You can heat it, cool it. It doesn't get dangerously brittle. This is your structural sections, nuts, bolts, rivets. It's cheap and reliable.
But not very hard. You couldn't make a chisel from it.
The edge would just fold over on the first hit. For that, you need to step it up.
To medium carbon steel.
Now you're in the 0.3 to 0.8% range.
Yeah.
You're trading some of that easy workability for more strength and hardness.
So things like axles, maybe? Hammerheads?
Perfect examples. Axles, wire ropes, agricultural tools, spanners, things that need to be strong but might still need a little give.
And then we get to the top, high carbon steel.
Now we're at 0.8 to 1.5% carbon. This is what you'll hear called tool steel.
Because you make tools out of it.
Right. It's very hard, resistant to abrasion, and this is the most important part. It can be heat treated to hold a razor-sharp cutting edge.
So our drills, taps, files, chisels.
All high carbon steel. But again, there's a trade-off. As carbon and hardness go up, ductility goes way down. High carbon steel is brittle.
So that old workshop rule, never use a file as a pry bar.
Is based in solid metallurgy. It won't bend. It'll shatter.
A good safety tip. Now, before we leave the ferrous world, it's not just about carbon, right? There are alloy steels.
Oh, absolutely.
Yeah.
The special forces of steel. You can add things like chromium to make stainless steel, which resists rust, or manganese for extreme toughness, like in railway tracks. That's a whole other deep dive.
Right. So let's cross the border. The non-ferrous world. No iron allowed.
Yep, a totally different set of rules here. Generally non-magnetic, and they each have their own kind of superpower.
Okay, let's run through the main players. First up, copper.
The reddish metal. Soft, easy to work with, but its real talent is conductivity.
Electricity and heat.
Both. That's why it's in all our electrical cables, motor windings, soldering irons. You don't use it for strength, you use it to move energy.
Next, aluminium.
Or aluminum, the lightweight champion. Very low density, but it has a little trick up its sleeve that every welder needs to know about.
The oxide layer, I've heard this is a nightmare.
It can be. The metal itself melts at about 660 degrees Celsius. But the instant it touches air, it forms a skin of aluminum oxide. And that skin melts at over 2,000 degrees.
Whoa. So you're trying to melt the inside, but the outside is a solid box.
That's the problem. If you don't clean it off meticulously before you weld, you get all sorts of defects. It also suffers from something called hot shortness.
Hot shortness. Sounds like it has a temper.
You could say that. As it gets hot, it doesn't get soft gradually like steel. It holds its strength, holds it, and then suddenly just loses it all and can collapse. But its lightness is why we use it for aircraft and gearboxes.
Moving to the other end of the weight scale. Lead.
Very heavy, very dense, and very soft. You can scratch it with your fingernail. Its superpower is corrosion resistance.
Even against acids.
Yep. So it's used for things like cable sheathing and, because it's so dense, radiation shielding.
And last on the list, zinc.
Zinc is the great protector. We mainly use it as a coating on steel.
Galvanizing.
That's the one. The zinc corrodes first, sacrificing itself to protect the steel underneath. Think of corrugated roofing.
Okay, but just like with steel, we often mix these to make alloys, right?
The recipes are key. Take brass, that's copper mixed with zinc, stronger than copper, casts well, used for water fittings.
And bronze.
Copper plus tin, harder than brass, great for wear resistance, so you find it in gears and pump impellers.
And solder is tin and lead.
For that low melting point. And one more, duralumin.
Right, the aviation one.
It's aluminium plus copper and magnesium.
Yeah.
You get the lightness of aluminum, but with much higher tensile strength.
Okay, so we know what they are, but now the real test. You're on the workshop floor, you find a random offcut, no label. How do you know what you're holding?
The artisan's eye. This is so important for the ARPL. There are 3 quick field tests: sound, spark, and color.
Okay, the sound test. You hit it with a hammer.
If it's cast iron, you get a dull thud. Remember that damping capacity just goes thump.
Mild steel.
A medium metallic ring.
And cast steel.
A much higher pitched clearer ringing sound. So thud versus ring tells you a lot.
All right. Method 2, the fireworks display, the spark test.
This takes practice, but it's a great skill. You touch the metal to a grinder and watch the sparks. The carbon is the fuel.
So cast iron with all its graphite?
It gives off a really small, dull red stream. Very short sparks, not many of them.
And mild steel.
That gives you a long, white stream of sparks. Much brighter.
But the real show is high carbon steel.
Oh, yeah. High carbon steel gives you a bushy stream with these little explosions at the end of the spark trails. We call them starbursts.
Because the carbon is burning up.
It's popping. If you see starbursts, you've got high carbon steel, no doubt.
Okay, that's really cool. Finally, method 3. This one isn't physics, it's just memorization. SABS color coding.
You have to know these for your assessment. In the industry, metal bars are painted on the end for identification.
Here at Pop Quiz, I'll say the metal, you give me the color. Mild steel.
Orange.
High carbon steel. I use a little trick for that one. Brown is hard ground, to remember the hard steel. Cast steel.
Blue.
Stainless steel.
Black.
That's a tricky one. You'd think shiny, but it's black. Structure steel.
Red.
And finally, pipeline steel.
Great.
Seems like a lot, but mixing up your orange mild steel and your brown high carbon steel will either ruin your workpiece or destroy your tool bit.
Or give you an automatic fail in your trade test. It shows you haven't planned the job properly.
So, to wrap this all up, we've gone from the iron giants, seeing how a tiny bit of carbon divides steel from cast iron.
We saw how that carbon creates everything from ductile, weldable, mild steel to hard, brittle tool steel.
Then we toured the non-ferrous world copper's conductivity, aluminum's lightness.
And we learned how to tell them apart on the workshop floor, the thud of cast iron, the starbursts of high-carbon steel, and those critical SEBS colors.
And the why behind all this is that the material dictates the method. You can't treat them all the same.
You really can't. You try to weld cast iron like mild steel without preheating, it'll crack. The material is the boss.
Before we go, here's a final thought for you to chew on. We said gray cast iron has amazing compressive strength and it absorbs vibration. So why don't we build bridges out of it?
That's a great question. It gets right back to the core properties.
A bridge isn't just being squashed.
It's being pulled. It's under tension. It flexes. And what happens to cast iron when you pull it?
It snaps.
There you go.
Something to think about. Good luck with your ARPL prep. Keep learning, keep practicing, and respect the material.
And stay safe out there.
Until next time.